That's great. Okay, yeah, so I'm Alessandro Manzotti, and I'm currently a PhD at the University of Chicago, but I'm moving to Paris in the fall. I want to start by thanking the organizer. The conference is so good, I can't blame you for putting me as a first speaker after a conference dinner. But it's great, really. So I'm going to talk about kind of the story of my last 2 year of PhD. Which is working on delensing real data from SPT, CMB B mode. But I want to start from thanking the entire SPT collaboration that kind of adopted me in these past 2 years, and in particular these two folks here that really helped a lot in this kind of effort that I led. One is Carol Story, which is in the audience, here to just get all the hard questions from me. And Kimi, which is home doing the hard work, should have been here speaking. So what was the point of these things? And we sit down, I think 2 or 3 years ago, and there was a lot of hype of like detecting primordial B mode, and we said, yeah, we should do it. We should really do delensing because it's crucial. And since I would say a year ago, no one has ever done that on real data. So I'm going to tell you the story and tell you what we have learned and what I think. And we think that the field can learn and do in the future. I'm going to kind of build my talk on Anthony talk on delensing and Blake a little bit. So I'm going to skip a lot of introduction, but feel free to stop me and ask questions if something is not really clear. Okay, so why is delensing important? So why is this green curve on top of what we all want to measure important? Well, because you can see it as a 5 microkelvin arc minute on top of your maps, and so if you're pushing hard, as Clam and others are doing, to reduce your instrumental noise, once you get close to that level, now it's really important to also delens and not just make your instrument better and better. I just want to point out that it's different from foregrounds. Well, obviously because you cannot use kind of multi-band, multi-frequency approach, because dancing is the same at all frequencies. But also because we know pretty well what this green line is, right? There is no weird astrophysics involved. It's just linear physics that we know and love. And so we could actually do what people have done so far, which is fitting both the green line and the blue line. The point is, if you do that, you're just using kind of average on the sky information about this guy. And so now the cosmic variance, so the fact that actually those B modes, lensing B modes, can be actually slightly different on the patch you're observing, is actually limiting your power to constrain the amplitude of sigma r and all those primordial B modes, right? Because now if at the point here that is slightly higher, you cannot distinguish from a contribution from primordial B modes or some kind of statistical fluctuation of your lensing B modes. Right, so the problem is the variance of the signal, and I think from what I told you, it's pretty clear that the solution is not just using the average over all the sky, but actually using actual maps of the patch that you're observing. So to do delensing and to deal with this lensing component, I think everyone agrees we need two ingredients. We need a QU map, so what is lensed, and we need a tracer or an integration along the line of sight of structure, which is the lenses that are lensing it, right? So this is the starting point. And I want to start saying here that the way you will use these two ingredients to deal with delensing is not set in stone yet, right? The field is working on it, we're looking for optimal way. People have done a slightly different thing, and so this is a point to keep in mind. But I'll tell you what we did with SPT. We decided to do this, and we decided to delens SPT pole data. So I feel kind of sorry that I don't have like a drone video here, but the picture is good, right? So it's a nice picture of SPT, which is a ground telescope at pole, and I'm going to focus on this part of our kind of campaign. Which is we took polarization data for 5 years, and we decided to start to test the technique delensing just 2 years of data, and you're going to hear a lot more about the wonderful things we did with SPT pole from Kyle, and actually SPT pole is done, congratulations to Haz, and we're actually deploying and working on SPT 3G, and Sasha will tell you more about that. Okay, so we delensed the first 2 years of data, which correspond to 10 by 10, so 100 square degree patch on the sky. I think it's important here to emphasize now, and I will tell you more about that actually the entire SPT pole area is a 500 square degree patch. And by design, it overlaps with bicep cap, right? So, and this will be important at the end of the talk. So we decided to delens here. We sit down in our office, I remember that, and we said, well, we have everything we need, right? Because we can get a good estimate of what the structures are on our patch in the sky using the cosmic infrared background from Herschel. So you can take Herschel maps at 500 micron, you kind of filter them, assuming a model, and you can get a good estimate of what the structures are. And then we had Q and U maps, or their Fourier transform equivalent E and B mode map that were tested well by we publish those maps, so we test for systematics and all of that. And one thing to keep in mind, again, another thing to keep in mind is that our B modes are quite noisy. It's 10 microkelvin per minute. So it's higher than this kind of limit of 5 microkelvin per minute, which is what lensing will give you. So this is important, again, for the future. But again, these are the maps we had, and we thought, well, it looks quite easy, right? We just have everything, we should put everything together. It's like a 6-month project. I should really find a new project for my thesis. This is not enough. And so after 2 years and a half, I'm going to tell you that we're almost done. We're almost done with all the publication, and I'm going to tell you what we did. The way we use those two ingredients that I told you at the beginning is we take the Q and U maps and we form E mode and B mode. So we move to Fourier space. We took the lensing map that we had, and using the E mode and the lensing map, we actually convolve them and we get a B mode template, right? So Fourier space, we have our measurement of B mode data that contains, again, primordial signal, lensing, and definitely noise. We took our best B template, we subtract them in Fourier space, and we took the power spectrum of it. And what you would expect, or what you would like to see, is this green line going down, right? Now, I think it's important, because I mentioned that at the beginning, that we do not, and I think it's true, that this is not the optimal way to do it. Right? This is not the optimal way if you're looking for sigma r to do the lensing. But I think the reason we did it is this has to be a test of the technique on data, and so this is one of those things where everything you do wrong, and that's why it took 3 years or 2.5, show up. Because whatever you do wrong in this template, so whatever is there, but it's not in the data, once you do this subtraction, it's going to stay there, then you take the power spectrum, and instead of removing power, you're adding power. Right? So it's a very powerful technique to test that everything you're doing is correct. One important thing that we figured out, and that's kind of related to that, is that, for example, because of atmospheric noise, we removed a lot of modes in the direction of the scanning. And so, for example, before doing that subtraction, you should remove the same kind of modes from your template when you do the power spectrum. So this is one of the things we have learned. But let's move to the real data, so the final results. So this is the nominal analysis, so Kessler et al., right? The power spectrum of lensing B modes on our patch of the sky. So you see the data with the error bars coming from SINS. And we removed the template and we took the power spectrum again. And so what we would like to see, and we saw, is that as you see, the error bars and the band powers are going down quite significantly. So I will anticipate some of your questions because I think it's important. So the first thing you should ask me is, well, you told us the very important thing of all this business is that you want to reduce the variance. It doesn't really matter if you're removing power. The entire reason why we're lensing is to reduce the variance. And so if you look at these error bars, what's actually happening is that they're kind of reduced by a few percent, but they're almost the same before and after the lensing. Now, the reason is, as I said, that we're delensing maps that are 9 microkelvin per minute in noise, or 10, and so the big part of these error bars is coming from noise. So we do not expect to reduce it because we're not removing noise. But we're just reducing the small part that is coming from lensing. So again, we're testing the technique. We're not going to measure, primordial gravitational waves with SPT probe. What is the amplitude? How much power we remove? The way we measured it is we do the usual thing, like an NCMC fit, where everything is there. We fit for all the amplitude, and you can see that A length. So the amplitude of the Delensing B modes went down by almost 30%. So the power we remove is around 30%, and it doesn't matter whatever you put in this fit. It can be foregrounds, it can be dust. Nothing can mimic this thing. We're pretty confident that we're removing lensing and not foregrounds or not something else. Now, again, another thing you can say is, this power is going down, but it's compatible with the error bars. Are you sure you're delensing? Now, the right way to look at it is what also other people like Anthony did, is you should look actually at the different quantities, not the CLs, but the difference between the CL before and after delensing. Now, if you move to that space, you get something like these, where 0 means no delensing. And as you can see here, our results is pretty robust. You should get two things from this. So this is what we expect from simulations, and these are our data with the error bars. Now the error bars are smaller, because when you go to the difference, you're canceling noise. So as you can see here, we are compatible with what we expect from SIMs. We're not delensing more or less or in a different way. And when you look at these error bars, this is a 7 sigma detection in some sense, or a 7 sigma significant result of delensing. So we're pretty proud of it. And we test all this possible robustness, but I can tell you more later. Now, the future is going to be even brighter, because if you put these results into context, you might be kind of disappointed. Because this is a kind of a cartoon of what we got. So the scale is not the right scale, right? We would like to delens these scales here, where the beamers are kind of, we expect primordial beamers to be there. And also, the amount of power removed is around 30%. And as Victor and others told you, we're really looking for a 90% delensing, so we have to do better. Now, I don't have a lot of time to talk about this test, but I'm just gonna tell you, so we did a lot of simulations to validate our results. Real simulation with the noise from the experiment. This is another thing that experiments are doing, like Victor did, because we really need true sims. But I'm just gonna tell you what our learning from this, which is, the reason why we're not delensing really well right now, only 30%, is because we do not have a good map of larger structure. High redshift enough to really recover those lenses that are lensing the CMB. And this thing will change because people like Daniel Lenz and others are working on better CIB map, but more than that, because internal CMB is getting better and better. We have heard from Blake, we will learn from Kyle again, so we are going to be able, with the CMB itself, to reconstruct that maps and do a good job. The second thing we learned is that once you have a very good phi maps, then a lot of other details comes in. And this is exactly the regime of removing like 80–90% of the power where we're going to be in CMBS4. So to plan CMBS4, we have to be careful at what kind of power we remove, what kind of mode we remove, because of atmospheric noise, what kind of overlap we have, are we delensing in the same patch, and all those kind of things. And I can tell you more about that. So what about I think are the 3 things the field should do? First, getting a better B-lens template, and we're going to do it for the reason I told you. The second one is using the template optimally, right? This was a test. We want the nature or whatever to prove us wrong. So we choose the least optimal thing to do. But now we have to notice something else. Maybe what Marius is going to tell us is the right way to go. Maybe there is something else. We should think about it. And I'm humbly adding something to Lyman's list. If you delens, you have to know what is left. Because if you delens, but something is still there, and you claim that that is primordial gravitational waves, but it's some kind of foregrounds leaking into your template, well, that's bad, right? So we really want to know that better. So I just want to give you 2 things to kind of stay tuned in the future. I know you all look at Archive every day, but maybe you're going to miss it. I think what we're trying to do is, the goal we have is this. The first thing is we still have 500 square degree of data, right? We just use 1/5 of it, and we want to delens also that. And again, as a test for the technique. So maybe something like what Mario's or this likelihood technique is a good way to test this on SPT data, put it together, lensing from the CMB and from the CAB as Planck is actually doing. But the final goal, kind of the dream we have in mind, is Bicep Cat is on the same patch, and they're doing the real job, right? They're really looking for primordial beamers. So the final goal is to put together our expertise, our maps, and make delensing really the thing that will improve your sigma. Not just the test, but actually the important thing. And thanks for being here so early. I'll conclude here. and get questions.